Heading to our next talk, program analysis via multiple context-free language reachability, and our speaker is Giovanna, Kobus, Conrado.
Okay, nice. You guys can hear me. Hey everyone. So today I'm going to be talking about a nice expressive framework for program analysis. And I'm going to start, I'll start talking about just language reachability more generally as a framework for static analysis and how do we use it. And the problem that I'm going to use as an example here is essentially we just want to know if the value of like some variable y can flow into some variable y, x into y. And this is like, you can see how that's a common problem we might want to solve in program analysis, right? Using data flow analysis. In our experiments, we're going to be talking about taint analysis. So basically, if a user has access to a certain set of variables, they might like not, we don't want them to be able to affect some like private data, right? So data dependence analysis, alias analysis. So how do we solve this problem? Let's look at this like very simple segment of code here. And we want to know if the value of a variable a will flow into the c that I've defined. And this is the case here, right? Like a goes into b, b goes into c, awesome. But how would we solve this type of problem? I think an intuitive way to start would be to make a little graph. We put each of these variables as a vertex. And if the value of one variable flows into another, we add an edge between them, right? So a goes into b, b goes into c, a reaches c. Therefore, a affects the value of c. But let's see what happens now when we have like slightly more complicated programs. So here, for example, we have like a couple of function calls. And we want to know which variables affect the value of b. If you look at this function next2, we have this a. A is going to go into next, the function next. So a is flowing into x. And then that x flows into the return field, right? And then that return field flows back into b. So a affects the value of b. And if we create a graph, the way that I was defining before, indeed, a does reach b. So that's good. But we also have that sneaky function next3 here. And that makes it so that c also goes into next and returns into b. So essentially the problem here is that we're not keeping track of where our functions come from. We're not keeping track of these function calls and these return sites. And we need to be able to deal with this issue. Otherwise, we're going to have lots of false positives. And the way we're going to do this is by adding parentheses. So every time that we have a function call, we're going to add an open parentheses corresponding to the call site. And then when we return, we must return to the same call site, right? So here, for example, when I go from a to x, I have this open parentheses 2. And then when I go from the return field, I have to close this parentheses 2. And using parentheses here and looking at these well-nested paths essentially allows us to have, you can call function within a function. You can call function return and call another function, right? The parentheses model very well what are like our good paths here. So we're looking at like which words form when we go from a to b. And notice that now C to B is not good anymore because we're opening the parentheses 3 and we're closing parentheses 2. That's not well nested. And a similar problem arises if we have compositive data types. So here, for example, we have this point, which has a field x and a field y. And A flows into the field x and the field x flows into C. And we want to keep track of the fact that they're flowing through this field x, right? Because, for example, B flows into P as well, but flows into Y. So B does not affect the value of C. So yeah, A reaches C here, but B also reaches C, which would give us a wrong taint. And the way that we fix it, now we use brackets just to differentiate them, but it's essentially the same fix. And this allows us to do the same modeling as before. So you can go, P.x could go into another field of another thing and then return. But it allows us to like restrict paths into field-sensitive paths. And generally, the way we solve these problems is with this general framework of language reachability, which is essentially the problem of like, given a graph G, I want to know which pair of vertices can reach each other through a path that is in this language L. And this is just like a general framework in static analysis, right? Here we have like this thing with parentheses, but you could be representing pretty much anything. In this case, our G is going to be this graph on the objects of the program, and our language L is going to be the language of well-nested parentheses, or well-nested brackets, which is the Dyck language. And the nice thing about the Dyck language is that it's a context-free language. It can be written this way. And like, I also want you to pay attention to like slightly unusual notation because we're going to be expanding on this later. But basically what we're saying here is that the Dyck grammar recognizes the empty string if it recognizes a string x, it also recognizes x with matching parentheses around it. And if it recognizes x1 and x2, which is that comma there, then it also recognizes their concatenation. That's how we define well-nested parentheses. And the reason why we like the fact that the Dyck language is a CFL is that when language reachability, when the language is a CFL, can be solved in n cubed time, which is polynomial. It's good. We're happy with n cubed in this case. But what about when it isn't a CFL, right? What about when we're dealing like with multiple languages at once, when we have like more complicated stuff? That's what we're going to be working with here. In particular, let's look at this case. If we have an ultra-complicated program that has both functions and like fields, composite variables, then we have to keep track of both the parentheses and the brackets. So essentially, we want to see a path from A to C is valid if I take the labels, I form a string, and if I look at this resulting string, if I like squint my eyes and I only look at the parentheses, that is well-nested. And if I squint my eyes another way and I only look at the brackets, that's also well-nested. But notice that like the parentheses and the brackets, they can be like interleaved amongst themselves, right? They can like deal uglily with each other. This is called the interleaved Dyck language, which is the interleaving of the Dyck language. And the problem here is that interleaved Dyck language reachability is undecidable. So we have no hope of like solving it completely, which means we must approximate it. Most of previous works has been focused on giving over-approximations of the interleaved Dyck language. A problem is that we don't have under-approximations, so we don't know how good these over-approximations are. In this work, we're going to focus on presenting an under-approximation for this. So let's talk a little bit about multiple context-free language reachability, which is what this paper is about. So context-free languages are a very restricted set of the greater class of context-sensitive languages, right? Includes things like Dyck language, includes things like the English grammar is a context-free language, kind of. Palindromes are a context-free language, but even things that for us are kind of simple, like just the language of words repeated twice, or Dutch, they cannot be expressed as a context-free language. So what we're going to do here is we're going to define the set of multiple context-free languages, which are a generalization of context-free languages. And the reason why we like it is because multiple context-free language reachability is decidable. And it's already a more expressive framework than context-free language. And what we're going to do is we're going to take the interleaved Dyck language, we're going to put it in a box, and we're going to squeeze it really hard, and we're going to try to under-approximate it through an MCFL. And just like to give an idea of the expressive powers of MCFLs, it is like already much stronger than usual generalizations that you may see of context-free languages, such as head languages or tree adjoining languages. Okay, so what is an MCFL? What does it look like? So let's look at this language here, which is a language that cannot be expressed by a CFL, which is word1, word2, hashtag word1, word2, word1. So something like Denver, Colorado, hashtag Colorado, Denver, right? So an MCFL is going to be a language that can be expressed by a multiple context-free grammar, just like a multiple context-free language can be expressed by a context-free grammar. And it's composed of rules. We have these 4 rules here, and the predicates. In this case, our predicates are this A and S. So this A, epsilon, epsilon essentially means that like now, as opposed to a context-free language where each predicate recognizes one string, in this one, our predicate is going to recognize a tuple of strings. So in this case, we have a dimension 2. And so we can recognize 2 strings simultaneously, right? And then in this production rules here, we have that like, if A recognizes the tuple x1, x2, then it recognizes x1 with a 0 in front and x2 with a 0 in front. Similarly, if it recognizes x1, x2, it recognizes x1 with a 1 in front and x2 with a 1 in front. And what's going to happen here with these rules is that essentially through starting with 2 empty strings and through repeated applications of the second and third rule, our strings x1 and x2 will like grow simultaneously. So in the end, our predicate A will recognize every pairs of string x1, x2, such that x1 is equal to x2. So every pairs of strings that are the same. And then we have this last rule here, right, in which we say that if A recognizes x1, x2, so x1 equals x2, and A recognizes y1, y2, so y1 is equal to y2, then S recognizes xy, hashtag yx, which is the language that we were looking for before. And then here, we also introduce another kind of variable in this our DMCFLR, which is the rank of our multiple context free grammar. And the rank is going to be the most number of predicates in the right-hand side, right? So in this case, we have 2 predicates, x1, x2, ay1, y2. If we had like ax1, x2, ay1, y2, az1, z2, that's 3 predicates, our rank would be 3. You may notice that like when our dimension is 1, this is just a CFL. And also CFLs don't really have a rank. But in our case, yeah, we have like these hierarchies. So basically, for a fixed rank, the bigger the dimension, the more expressive our language is, the more languages we can represent. And if we fix the dimension, the bigger the rank, the more languages we can represent. So we have these 2 hierarchies here. Now we need to use this framework to approximate the interleaved Dyck language, right? So we have these strings in the interleaved Dyck language. So there are strings that if you just look at the parentheses, they are nice. If you just look at the brackets, they are nice. How would we under-approximate this, like using a CFL at first, right? Let's just think about under-approximations in general. Well, a possible way would be to make a CFL that recognizes well-nested parentheses, a CFL that recognizes well-nested brackets, and then we just concatenate the 2, right? This is a valid under-approximation because every string that is recognized by our CFL is an interleaved Dyck language. But of course, there are strings in the interleaved Dyck language that we don't recognize, which is essentially everything that has this interleaving. So how do we even capture that? The idea here is that we're going to use the dimensions as breaking points for our interleaving. So for example, this predicate P3 will recognize all strings on parentheses broken into 3 parts. And it's not hard to define rules such that like this is the case. Now that we have like this predicate that recognizes parentheses broken into pieces and bracket strings broken into pieces, we can define a rule to interleave them, right? So we have that like if P recognizes x1, x2, x3, and Q recognizes y1, y2, y3, we can just alternate them in our final string. Notice that this also has an interesting feature in that we defined a tunable language, a tunable grammar. So the more dimensions, the more breaking points we can afford, and therefore the more complicated strings we can express. And this grammar that I just described is kind of similar to bounded context switchings in terms of like recognizing these interleaved Dyck languages. But we are expressive in the sense that we can add more rules as long as we don't break the fact that it's another approximation. For example, if S is in the interleaved Dyck language, we can just insert it arbitrarily into anywhere, and we're still going to have a sound under approximation. And now, like with these rules, our generalization is much stronger than bounded context switching. So even for like 2 dimensions, we can recognize strings that have an unbounded number of context switching. So for example, this Lariagu string, we can recognize it with 2 dimensions by adding some of these rules. OK, so now we need to solve MCFL reachability. And how do we solve it? It's in the paper. But we basically generalized the algorithm for context-free language reachability. And we did so by defining a normal form for these multiple context-free grammars in a similar way that you have the Chomsky normal form for context-free grammars, right? And we also generalized the standard CFL reachability algorithm to work with multidimensional predicates. This algorithm that we designed, it runs in O of n to the d times rank plus 1. So of course, like the more dimensions you have, the more time you're going to take. And we have proved lower bounds for rank 1 of n to the 2d. So that basically means that, like, indeed, as we increase the dimensions, we do need like an n square factor. We cannot like get rid of it. And how does this perform in practice, right? So we worked with this tent analysis benchmark, the benchmark for scalable and precise tent analysis for Android. And this gives us a graph on the objects, right, on these variables. And we must report the number of pairs UV such that U affects the value of B, right? So basically such that there is a path from U to V that is in the interleaved Dyck language. And what we're going to do is we're going to offer our under approximation, and we're going to compare it to the best available over approximation. So these are benchmark. These are basically simplified versions of like Android programs. But you can see that they already have like a decent number of nodes and edges, right? They're not tiny, tiny graphs. And these over approximation columns show how many things, how many pairs of variables were reported by the best available over approximation. And in our results, These are the number of paths that we reported for running our approximation in 1 dimension and running it in 2 dimensions. And these ones that are grayed out, the ones that are in bold, they are the benchmarks for which our number coincides with the over-approximation. This means that for all these bolded benchmarks, we have found the optimal answer for this undecidable problem, which shows that even for dimension 2, we offer like a really good under-approximation, right? So it's optimal for 8 of the 11 benchmarks. And even for the benchmarks that is not optimal, we find the great majority of reachable paths. We conform 97.9 of the things reported by the under-approximation, which means that the number of uncertain pairs, which a couple of years ago would be like half the pairs, are now reduced to less than 2.1%. And then just like to show the runtime, our runtime is comparable to the over-approximation. OK, so in conclusion, in this paper, we've developed an algorithm for MCFL reachability, and we modeled interleaved Dyck reachability as this tunable CFL, right, that can have any strength we want, but with paying like runtime. And we also proved experimentally that this grammar is a very good approximation, and that often produces optimal results for real-world benchmarks for this undecidable problem, which again is very exciting. But this paper is not about interleaved Dyck reachability, it's about MCFLs. So I think most importantly, we showed here that MCFLs are a valid tool for static analysis, that if you're trying to solve some language reachability problem and you end up with a mildly context-sensitive language, you can use MCFLs to try to solve your problem. And these algorithms, they are practical, and we've offered like a foundation on how you can use them in the field. And that's it. Thank you very much.
All right, so we have time for one or maybe two quick questions while the next speaker can already prepare the laptop. Any questions? Oh, yeah.
Hi, thanks for the talk. Maybe this is a naive question, but I was wondering, when you have like the p.x and p.y, why can't you model that as like two distinct objects and avoid the brackets?
So that's the access path abstraction. Like that is a valid way to model, and that's a valid like approximation of the program. But it fails to model some more complex things that may happen. For example, you may have an object that like has two fields of itself, right? A pointer that carries two pointers, or when you have pointers, you can have like loops. And so essentially, you could do that. Oh, sorry. But you would have to stop at a certain point. So it would still have like an inherent approximation tied to it. Yeah.
All right, let's thank our speaker again.